Hello, welcome to an in-depth analysis of Google Maps path planning algorithm and attempting to answer the following core question. How does Google Maps path planning algorithm differ from a standard distance transform? To answer this, the following extrapolated questions must be answered. What fundamental algorithm does Google Maps use? What factors do Google Maps consider when planning a route? And how does Google Maps account for these factors in an algorithm? To best compare the differences between Google Maps and a distance transform, a distance transform script should be developed such that its resulting path can be compared to Google Maps. This will emphasize any key differences between the algorithms. To make this distance transform algorithm, the MATLAB script will need to take a real map image as an input. Using color thresholding from the MATLAB image processing toolbox, this image input can be processed into a logic image. From this logic image, an occupancy grid can be defined. This is as simple as defining each cell as either drivable, 0, or not drivable, 1. From this occupancy grid, an unsolved distance transform can be defined, substituting zeros with infinity and ones with not a number, or nan. Furthermore, the goal position can be set to 0. To begin computing this distance transform, we need to define a 3x3 window, W, of the closest infinity to the goal. Similarly, a matrix M needs to define the cost to move in each direction. To keep this example simple, we will use Manhattan distance. In Manhattan navigation, you can only move left, right, up, or down. Therefore, to get to the top right block, you have to move up, then right, which is considered 2 movements. Therefore, the top right element has a cost of 2. This is different to a Euclidean distance, where moving to the top right can be done in one diagonal iteration, with a cost of approximately 1.4 movements, which is the square root of 2. So using the formula outlined here, we can find the element E. Similarly to the previous slide, we will move the window to the nearest infinity and follow the same computational process for this element. This process will then be applied to the entire map until all reachable blocks have had a distance defined. Now that we have a fully populated distance transform, we can now define the shortest path. Similarly to computing the distance transform, we can define a 3x3 window W to find the smallest element X. Using the outlined formula, we find the smallest element in the window. In other words, the most efficient movement towards the goal is to go to 10. This process can then be repeated by recentering the window on the smallest element. Now the shortest Manhattan path is determined as seen by the green path highlighted here. Finally, we can apply the same methodology through a MATLAB script to a real-world map. After generating the experimental script, here are the final conclusions. Conclusion 1. Google Maps uses a similar algorithm to the distance transform method. As can be seen, both algorithms chose the exact same route, which shows that fundamentally Google Maps uses a variation of the distance transform. As seen here, the distance transform reports 4,367 meters to the goal, whereas Google Maps reports approximately 4,700 meters. This can be explained by looking at an intersection. The distance transform algorithm will always go the absolute shortest route, even if that is over the wrong side of the road, whereas Google Maps will always calculate routes which maintain proper lane placement and therefore will always be longer. Thus, the second conclusion can be drawn that Google Maps can interpret lanes. The third and most obvious conclusion is that Google Maps can incorporate road conditions into its algorithm and will always return the quickest path rather than the shortest. This takes into account live traffic data as well as road speed limits and current roadworks or delays, which can completely change the optimal route. As can be seen by this snippet, there are 3 options to get from point A to point B. The quickest route is 13 kilometers longer than the shortest route, however, is 3 minutes quicker than the shortest route. Finally, we can have a look at how Google Maps might incorporate this data. First of all, lane interpretation. This appears to be the simplest difference to solve. After defining the occupancy grid, a post-processing function could be run, which grabs the width of each road in the map and turns the road on the right-hand side in the direction of travel into an inaccessible area, as seen here. Similarly, a different method can be applied to account for road conditions. A common method is to add additional weighting to the distance transform. For example, let's assume 1 pixel represents 100 meters, and there are 2 different speed-limited zones. White pixels represent a standard road without any disruptions, so you can travel 55 kilometers an hour, or 200 meters a second. Brown pixels represent a busy road, either with congestion or roadworks, so you can only travel 28 kilometers an hour, or approximately 100 meters per second. Knowing this, we can calculate how long each pixel will take to travel through, and therefore we can further compute the distance transform into a weighted transform. This will be in the unit of seconds as opposed to distance. We can then substitute our knowledge that white pixels take exactly 0.5 seconds to traverse, and brown pixels take exactly 1 second, and compute the weighted transform. Using the same path planning algorithm discussed previously, we can then see that the obvious path to reach the end goal avoids the disruption, just as Google Maps would. Coming back to the original core question, the following answers can be provided. Google Maps uses an algorithm like a distance transform. Google Maps considers lane positioning, roadworks, and traffic congestion. Google Maps potentially could be using the additional two methods mentioned in the previous slides. Thank you for listening.